Hello. All right, so here we have a parallel plate capacitor, just a couple of metal plates attached to a voltage source, and there's a little hole on top, right there. Okay, it's 2D picture, you can't tell, but that's just supposed to be like a little circular hole. And let's say we know that the voltage is like, I don't know, 100 volts. Okay, I'm going to use this crazy thing to launch an electron. So here's my little electron starting out down on the negative plate where it doesn't want to be. I'm going to launch that electron straight up into the air. Okay, so it's going to go get some velocity way up into the air, and at some point it would start coming back down. There's a little snapshot of it up there. So my question is, how high would this electron be launched into the air if this is on the ground here? So there's my ground. And the voltage is 100 volts. Alright, so just let's finish up the picture here. We'll get that onto the picture. What we're looking for is this height, right? Okay, so, it kind of looks like it could be a kinematics problem, but usually at this stage you can actually go with energy instead of kinematics. If the problem asks for time, you might need kinematics, but when we have these sort of quantities and we're looking for a distance or a velocity or something like that, you probably want to go with energy. So let's start out with the conservation of energy. The initial energy plus the work done by non-conservative forces is equal to the final energy. Now remember, non-conservative forces, that'd be like friction, wind resistance. Well, this electron is probably not going to encounter that much wind resistance. There's no friction, so like in many of our problems, we're going to zero out that. And it's just pure energy conservation. Initial energy equals final energy. Okay, so let's see. Well, why does this thing have energy initially? Well, it doesn't want to be there, right? The electron, it's sitting on a negative plate, and you'd have some resistance if you tried to push this thing down. It'd be sort of like trying to push down a spring. So there is an electric field. Remember, electric fields point from positive to negative. That's being formed by this potential difference. And it looks a little bit backwards, but remember, electrons go against electric field lines. So although the field lines are pointing down, that means the electron is going to want to shoot up. So since it's in this field, it has electric potential energy due to, well, you could say due to this field, or you could say due to the potential difference that it is in. So I'll put that in as electric potential energy. And that's the only kind of energy it has initially. It has no speed. It's at rest, if I didn't say that. It's just sitting there until we let go or whatever. And it's at the ground, so there's no gravitational potential energy. In the end, if we're looking for the maximum height it gets to, well, we know at that moment the velocity will be 0, right? Let me capitalize my other v's here. At that moment up there, the velocity is going to be 0. So no kinetic energy. It's no longer inside this electric field. There's no potential difference on it up there. So the only energy it's going to have is gravitational. Okay, so looking pretty simple so far. Let's just fill these in. Electric potential energy. Well, there are a few ways that we can write that, but since we have an electron, well, it's probably fair game to look up the charge and mass of the electron, right? Since we have the charge and we have a potential difference, let's use this definition for electric potential energy. Okay, and that's equal to our gravitational potential energy, which is mgh. Let's see, that's the charge of electron, mass of the electron, and all we need to do is solve for h, right? Divide over the mg. We get the answer is the charge of electron times the potential difference it's in, divided by the mass of the electron and the acceleration due to gravity on the planet we're on, is equal to the height we'll get to. Okay, so I don't know, sounded like it could have maybe been a tricky problem, but as you can see, we did it in like 3.5 lines here, so not so bad.